So on day one, I mentioned, who's got it all the way up like that? On day one, I mentioned this course takes 7 hours a week outside of lecture and lab at a minimum. I think some of you at this point are probably starting to believe me on that one. And we're still ramping up a little bit. So just a quick note on that. We covered objects and classes last lecture. And there's a lot of content that needs to be covered in this class. We got to keep moving. We're moving on from objects and classes. We'll still see some more examples of that as it relates to the newer material, but we got to move on. So you have office hours, the lecture recordings, review session tonight, 4 to 6, tomorrow 4 to 6, Friday 4 to 6. You have a lot of opportunities to catch up. There's Piazza. Feel free to ask your questions. If there's something that's not quite gelling with you, make sure you're on Piazza, especially if it's a conceptual question. There were a lot of concepts covered in Friday's lecture, and every question we get on Piazza seems to be, how do I do this lecture question? If there's something you don't understand about what was explained in lecture, those are perfect Piazza questions. Those are the ones we really love to answer when it's I get this error message. What do I do to get through this assignment? Those are less interesting and less helpful answers to y'all. In office hours too, hey, when you explain classes like this, I didn't really understand what a constructor was doing. Can you explain that to me? Those are great questions. Those are going to serve you better down the road too. But we got to move on. We're going to start talking about model of execution. So the lecture question today is a lot of objects and classes still in these next lectures, but we're going to look at how memory is managed by our programs and the implications of that to our programs. So what does the way an object is represented in memory, how does that affect us as developers when we're writing programs that use objects will be one of the big highlights. And then in lab next week, you'll be drawing the memory diagrams, stack and heap, as we'll start seeing today. So to that end, the lecture question, write a class named team, which is going to store the strength of the offense and strength of the defense for a particular team, and also store its score all in state variables, and then a referee object that can work with these teams and kind of officiate a game is what we're simulating here. So the referee can officiate a game between two teams. It'll take their offense and defense into account and then set their scores equal to their offense minus the opponent's defense, with the exception of they can't have negative scores. And then a declare winner, which is going to take two teams as references. So we have a method that's going to take two references as parameters, references of type team, and then return the team with the higher score. So assuming that they already played a game, who's going to be the winner based on their score variables? And if it is a tie, just one edge case, if it's a tie, return a brand new team with offense and defense both set to 0. Just some way to indicate that there was a tie. I don't know which one to return. Question?
You don't have to enforce that there's no negative scores allowed? Do you have to enforce it?
You should enforce, when you set so when the two teams play each other, you're going to take this team's offense minus this team's defense. If their offense is less than the defense, set their score to 0 instead of negative. So for example, if two teams have very weak offense and very strong defense, and they play each other, it's going to be 0-0 at the end of the game. So when you declare a winner, you don't want to give it to the least negative number. If you have negative numbers, negative scores, you're going to get jammed up in the declare winner. And a side note, I saw this question a few times, and when you're testing any lecture question or any objective, anything in the course, make sure you're only testing what's explicitly defined in the question, especially when we get to classes. This comes up a bit. If you create a class and I say create a class, team has a constructor that takes two ints representing offense and defense, but nowhere in this question did I say what those variables should be named. So if in your tests you're saying team.offense, assert team.offense equals 5 after you create a team with 5 offense, that's most likely going to cause errors in AutoGrader because you're relying on the chance that I also name that variable offense. So when your tests are ran against your own code, that's going to be fine because you named that variable offense. But what if I named it team offense or something different? It's only by pure chance that that might not cause an error in Autolab. Most likely it's going to because we just are going to name our variable something different. So when your tests are ran against my correct and incorrect solutions, if I have a different variable name there, that's going to be an error. That variable doesn't exist, and you're going to get the error in Autolab running your tests against correct and incorrect solutions. So if you do see that, that's the first thing to look at. Make sure you didn't test anything that's not defined here. The score variable, on the other hand, I do give that a name, so you can rely on there being a variable named score in the team class. All right, there was a question up here. Did I answer it?
Yeah, I just want to, so we're writing test cases for every lecture question regardless of.
My short answer is yeah, you're writing test questions for every lecture question, but I'm not grading them for this. It's not part of this assignment, so I don't have the write a test suite name this at the bottom. You still should. Do whatever testing will satisfy you to make sure that you know your code is correct. Don't use Autolab as your tester. But for this particular question, I'm not forcing you. I'm not requiring it, and I'm not assessing it. So for this one, you're just going to get either objective complete or your objective didn't pass all my tests. That's all you're going to see for this one. Okay.
So, I know not necessarily an issue with this one since there isn't test cases that's grading, but would the variable have to be public score if you did have test cases?
Yeah, would score have to be public? I guess I don't specify it specifically in this question, but it would be. As per when I talked about access modifiers, everything I have in every class is going to be public. So just by default, if I don't mention, it should be public. Yes?
If we have a test package, could we remove it before submitting to AutoGrade or remove it?
Nope. So the question, if you do write your test cases, you have a test suite to test this, should you remove it before submitting to Autolab? No, my grader won't look at it. It won't bother anything. And it's in general, if you want one, I know a lot of you like having one big project. To be honest, I do this with all my test submissions to Autolab as well to test the graders. Having one big project with every lecture question ever, that's fine. The one thing I always caution about this is if you have an error anywhere in that entire project, you're going to get errors on that lecture question. So you can have lecture question code that's perfect. The TAs and myself will look at it and say, that should be getting full credit with what's going on here. But if you have any code anywhere, so maybe you started the homework in the same project and you had a class to run to and you left it in a state with errors, with syntax errors, you had to go and then you work on the lecture question later, you still have those errors in your homework, well now your lecture question is getting jammed up too. So just be cautious about that, but you can have everything in one project. You can't have a single compiler error in the entire project though. Yes? It's not required. Yeah, we just talked about that. Yeah, the testing isn't required for this one. Absolutely, strongly, highly recommended. At this point in lecture, we're starting to get to, okay, I've showed you unit testing and the value of it. Now, if you don't have testing and you're submitting to Autolab 100 times, it just looks bad. It's not recommended. You can save a lot of time. Just in general as a developer, you can save a lot of time by writing your unit tests, even when somebody's not forcing you to do it. You save hours and hours of time by writing a couple unit tests. All right, let's get on to some lecture content here. We have a little bit of flex room on Friday, so if we don't get all the way through these slides, I'm not going to stress that. We can go a little slower through these ones, but not too slow. All right, interpretation versus compilation. This is a big difference. You're already feeling this. And there's some questions about Scala where you're probably wondering, like, oh, why does it do that? And you might just think at this point, well, it's just the way Scala goes, I guess. But interpretation versus compilation, this is one of the big reasons why 1.16 working with Scala is a little bit different than 1.15 working with Python and JavaScript. So interpreted languages and interpreted code is where you run your code and you have an interpreter just going line by line through your program. Starts at the top of the program or the main method if that's how it's set up, and just runs each line of code one at a time without looking ahead to anything. Just runs your code and just runs through it like that. Your code is being executed line by line. Compilation, on the other hand, before you run your code, before you can run your code, and you in fact don't actually run your code with compiled languages, your code is translated into code in another language, and then when you run your code, it's that language, the code, that translated code, that's actually executed. So you'll notice in Python and JavaScript, you'd have situations like this where you're running a program. This is how you write a main method in Python, if you're wondering. You'd have and classes in Python. I should take a step to just very quickly. This is a Python class. The constructor has to be defined as a separate method named init. And then when we create our objects, we don't use the keyword new. We just use that class name and call the constructor as a function. And Python will look for that underscore, underscore, init, underscore, underscore. The first argument has to be self, which is a reference to the calling object, and then whatever parameters we want after that. So we're going to create a new object of type runtime error example. We're going to add to the state. So we have some internal state variable named state, and it's self instead of this, same ideas. I don't want to get hung up on the Python syntax since I'm not testing you on that anyway. But we're going to set the state to some initial value 5 in this case, and we're going to add to that state. We're going to add 10 to it to get 15 in our state, and then just print the value of that state. We should expect this program to print adding to state and then 15. So that's what we expect. In fact, this runs just fine. Everything is good with this program. But if we go over to the same example with a slight difference, where instead of saying 10 as an int, we're giving it 10 as a string. Now we're trying to add 5 the int to ten the string, and we're going to get an error right here. We can't add an int and a string, and we're going to get an error on that line. But in Python, and the same behavior in JavaScript, our program does run. Because these are interpreted languages, JavaScript and Python are interpreted. All of 1.15 was interpreted. So when we run this program, this line runs, calls the constructor, this line runs, calls the method, this line runs. Adding to state is printed because our program does run, but as soon as we get to this line and we try to add two incompatible types, this is where we get the error, and this is called a runtime error. As our program is running, we get an error and our program crashes. Scala, Java, C, C++, and many others, these are compiled languages where we're not going to be able to get that same runtime error. We can still get runtime errors. It'll still happen. For example, in an array index out of bounds, we can get an error at runtime and our program crashes. And there are other ways to do it too. But the example we saw on the previous slide, which is recreated here in Scala, we actually can't run this program at all. So these are compiled languages, and when we compile our code, a program called the compiler is going to look at all of our code, our entire program in its entirety, and check everything for us. It's going to double check to make sure we don't add incompatible types. It's going to check all of our types to make sure our methods are returning the right types. It's going to do a lot of optimization as it's looking through, as it's converting this code, and just look over everything for us. So in this example, when we have that same error, we actually can't run this code at all, because when we go to compile it, which is before we even have a chance to run it, when we go to compile it, the compiler is going to say, hey, this method takes an int and you're giving it a string. I'm not going to compile this code because I don't know how to convert it into the other language. So it's a no-go. So in Python, in JavaScript last semester, you would be able to run your programs even if they had errors, and then the program would just crash when it got to your error. In Scala, you can't run. You're going to hit the run button, the play button. It's going to go to compile, and then it's not going to be able to compile, give you a compiler error, and then not even get to the point where it's running. So in this case, Oh, I got rid of my print line. But if we had a print line before this line, or even the first line of our main, if that's a print line, that print line, we won't be able to see it. It won't be executed. It never runs. And a compiler is very nice for us in that it helps look for these errors. That error in Python on the previous slide, we're going to have to find that error. Like, that's up to us as developers to find that error. Some IDEs will be helpful enough. It might spot that for us and say, hey, you might want to look into this. But that's up to us to spot. With compilation, and in this case with strong typing as well, the compiler is going to help us out. So if we ever have an error in our program, the compiler finds a lot of these errors for us. And raises our attention to it and lets us fix those errors, which can be very helpful. It can get frustrating at times too. The compiler stops you from even running your programs, but it is so helpful when it's scanning all of your code looking for errors, and it can flesh out a lot of errors before you release buggy code. Python, JavaScript, it's really easy to release buggy code and not find those errors, especially if you don't have thorough unit testing. Compilers fix a lot of our stuff too. Will fix a lot of our stuff. It's looking for optimizations all the time. So for example, we have an infinite recursive method here. As we'll see in the next lecture, this is going to cause what's called a Stack Overflow, the namesake of our favorite site. It's going to create an infinite number of variables named n and blow up our memory. In short, it fills up our RAM and crashes the program. This is one thing that the Scala compiler is going to fix for us. This code will actually run, and it'll run forever, and it won't crash. It won't run out of memory. It'll do some optimization on this code. So there are things like this where the compiler is looking out for us and trying to help us out. Also with mutable types, there are some things where if we're doing something really silly with string concatenation, the compiler can optimize that as well and help with our memory management. So the compiler can do quite a lot of nice stuff for us in terms of optimizations. Scala, the language that Scala compiles into, is called Java bytecode. This is the same code that Java compiles to. So Scala and Java, they're both compiled languages, and they both compile to Java bytecode. And this runs on what's called the JVM, the Java Virtual Machine. And the Java Virtual Machine is going to run the Java bytecode as an interpreted language. So Java and Scala, they're kind of hybrid, compiled and interpreted languages. So the Java bytecode is interpreted, but we compile into Java bytecode. This is whenever you see the new update to Java available, that's your JVM. That's JVM saying, hey, I got another update, and we always get these pop-ups, and they get annoying at times. But JVM, it's installed, billions of devices, probably most of the devices you own have Java, tell you to update Java. Anytime you see that splash screen, update your Java, you know you got the JVM installed on that machine, which means you can run compiled Scala or compiled Java code. So you can run the programs you're writing in this class on any one of those billions of machines out there. Since Java and Scala are compiled to the same language, we can use these two languages interchangeably. We can have programs that mix Java and Scala. We've already seen this with the string class. When I went into the string class last lecture, we saw that it was actually just the Java string class. We're just using Java there. And we'll do this later in the semester as well. We'll start mixing. We'll pull in libraries that are written in Java, specifically Java FX, and use some Java code in our programs. They can mix interchangeably like that. Yeah.
So you said that the Scala contains compiled, you can show the errors before you run it, right?
Mm-hmm.
So like, what about like, tell me about the squiggly line.
Mm-hmm. That's the compiler.
So like Python does that, or at least
So in Python, that's when you get the squiggly lines, the red lines that say you got an error here in your IDE. In Scala, that's the compiler, Scala compiler looking at everything in your IDE, doing some extra checks for you. In Python, it's not a compiler that's doing that, but a lot of IDEs have some features built in where it's going to do some checks, especially syntax. Like if your indentation is wrong in Python, the IDE is usually going to give you that squiggle and say, hey, look into this. But that's not a compiler that's doing that for you. That's the any features in the IDE itself. All right. Any other questions so far? Let's have a chat about memory. So when our code is running, what actually happens there, and for the next few lectures specifically, where is our data stored? When I create a variable, what does that actually do, and where is that value stored in my machine? And everything that we do in our programs is going to be stored on these RAM sticks. Yeah, these RAM sticks in your machine, and that's going to be where your programs are. It's on the RAM, on this silicone right here. You have something that looks similar to that. That's where everything is. This is effectively a giant array. We do have random access, so all the memory addresses in the RAM stick are addressed sequentially, and it's effectively like an array indice. Give me the value at the specific indice, and you can go to that spot on your RAM stick, or RAM sticks on one of them, and get the value stored at that particular memory address. So we have a giant array, and that's how everything's implemented. Even when we have different data structures, they're technically stored in a giant array. We like RAM because it's a lot faster than a hard drive. We don't use the hard drive for our program storage, just because reading and writing from a hard drive is very slow. We would only do that if we need gigabytes of memory or something. Well, I guess a lot of our programs, looking at you, Google Chrome, does take gigabytes of our RAM, but if we exceed our RAM, we could write to disk, but only if we absolutely need to. If we need to store things on disk because we can't fit everything that we need in RAM. But we'll use the sticks, and whenever we have to do file I/O, those are expensive operations. Reading information from a disk, very, very slow. If you're doing rhyming dictionary and you're reading that file 122,000 times, I think it is. If you have that reading the file within a loop where you're looking and checking every word, you'll get to that point if you don't know what I'm talking about. But if you're reading that file 122,000 times, you're going to time out in Autolab because those disk IOs are just way too slow. And reading that file that many times of that large of a file, prohibitively slow. Even with an SSD, SSDs are still much, much slower than RAM. Downside is it's a lot more expensive. If you want 16 gigs of RAM, it's going to cost you more than that hard drive, typically. More than that terabyte hard drive, typically. All right, so when we start our program, we're going to ask our OS, or rather the JVM is going to ask our OS. It's going to say, hey, I got a program starting up. I need some memory. I need some memory to be able to store this program. The OS is going to say, sure, here's a chunk of memory. This is yours. You're allowed to access this memory for this program. Before that and after that, anything that the OS has not allocated to us, we can't go reading those parts of RAM. We're going to get in trouble. The OS could shut us down if that happens. So we only have this memory to play with, whatever they gave us, and that's what we're going to work with. We're going to use this memory to create what's called the memory stack. And this is where we're going to store our variables for the program that we run. We're going to, every time we create a variable or a value, with exceptions we'll get to, but we're going to put them on the program stack and store them in this memory that's been allocated for us. There are this program data at the bottom. If you read the documentation I linked to for this, there's some other things that are happening there. It's a bit outside the scope of this class. I'm not going to talk about it. I think he'll talk about it in 220 at that point. I don't even know if they get to that part, but there's some extra information here, meta information about the program itself. We won't talk about that in 116. The stack is a last in, first out data structure. So we can think of this just like a stack of papers. We can access, we can add to the top of the stack. We can remove from the top of the stack, but we can't we can access in this case, but we can't remove or add in the middle of the stack. We can't just pull a piece of paper out of the middle of the stack, for example. And whenever we run a method, we'll see a more in-depth example of this on Wednesday. But when we run a method, we're going to create what's called a new stack frame. And a stack frame is like an isolated environment just for that method call. So if we have our program running in our main method, we're going to have a stack frame for that main method. Then each time we write another method, we're going to enter a new stack frame, which is almost like a completely separate program. And we can't access the variables from outside of that stack frame. So when you have a method call, if you have a main method and you create some variable x, and you call a method, inside that method you can't just say x equals 7. You can't access x because it's outside of that stack frame that you're currently executing in. Similarly, when you enter a new code block, so any block of an if statement inside a for loop, anytime you have curly braces and you're entering a new block, that has a little bit different scoping implications. So it's not quite the same as a stack frame where you can't access anything from outside of it, but if you have two variables with the same name, for example, the JVM is going to look inside that code block before it looks outside of the code block for a variable name. We'll see examples of that. That'll make more sense when we get to the examples. And when a code block ends, you've noticed this in 115. We'll talk about it a little more in detail now. When a block ends, all the variables that were created inside of that block are destroyed. So for example, you have a for loop and you say for I in whatever range, do some stuff. After that loop is over, after that loop's done, you don't have access to the variable I anymore. That variable was destroyed as soon as that code block ended, and along with any other variables that were created within that code block. Okay. With that, so that's a lot of information. That's a lot of what I want to show in this example. But let's go through this example and see what all that means and the implications of it. So I have this method, this program with a main method, just going to call this other method that I have. Nothing too complex going on here, but I want to compute the factorial of a value n. So I'm going to iterate 1 to n inclusive, and just multiply 1 by I for each value. So if I loop from 1 to n and just multiply all the values that I'm iterating over together, I should get n factorial out of that, and then I can return n factorial, and then I'm just going to print it to the screen. This example is language independent. I want to focus on the concepts of stack and heap and memory management. So I'm not going to talk about any specific language during this. I just want to show how the stack works. Though I believe this would compile as JavaScript, just by chance, just by the way I wrote it up. But that's just coincidence. So if you want to think of it as JavaScript, go for it. All right, so let's step through this program one line at a time and see what's happening on the stack. Any questions before we get started on this example? I am dope. All right. Yeah, this is a live class at a university. If anybody not in the class wants to enjoy it on Twitch, feel free. Go to CSE116.com if you want to check out some more content. Got to pitch my website there. All right. So let's step through the execution of this program and see what the hell is a memory stack. So when we first run our program, we have the very first thing that's going to be put on the stack, and the stack will grow from the top down. It's just how they're always represented in like any textbook, so I'm going to follow suit. It's because the memory addresses are going to start, like we're going to get the memory address here and forward, and we read those top to bottom. It's more visually representing pretty accurately what's going on in the machine. All right, so we run our program. The first thing that goes on the stack are command line arguments. So we have those argv or whatever we have. However, your language is taking in command line parameters. That's going to be in a parameter of the main method. So we're going to put those command line arguments on the stack. Again, 116, we're probably not going to mess around with command line arguments. And then we can start adding our own variables to the stack. So here I'm going to create a variable named I, assign it the value x. So that's going to get its spot on the stack, and it's going to take as much memory and RAM as that variable needs. So if this is a 64-bit value, it's going to take up 64 bits in RAM, and I'm going to get enough space, use up enough space to store that variable. So I have this variable named I, value 5. All that information goes on the stack. Very next thing, I have our first function call. We're going to start a new stack frame at this point. So we're creating a new stack frame, which means we no longer have access, as we go into this method, we no longer have access to the variables and values that were created outside of this stack frame. So we can no longer access our command line arguments. We can no longer access the value I, the variable I with value 5. We can't access those anymore because they're out of scope. They're outside of the current stack frame. So we don't even know that they exist anymore. Then we're going to create, the next thing that happens, create space for our parameters. We have the parameter n being assigned the argument of I, which was 5. So we're going to put n on the stack with the value 5 inside of this new stack frame. So our parameters are going inside that new stack frame, and that's the only variable that we have access to at this point. We can't access anything except n. We can't access this value I. We can't access our command line arguments. We can't access anything else. This is a whole, basically like running a whole separate program every time we have a method call. Until we get to heap space, of course, but we'll talk about that. Then we're going to create another variable, result, assign it the value 1. That's going to go on the stack. And we're always adding variables on that next available memory address on the stack. And we're never going to have remove a value from the stack unless it's the last one. So we're never going to have gaps in the stack. This is one continuous block of memory. It is effectively an array. We have one big continuous block of indexed random access memory. We're going to begin this loop block. So we have a new block. We have some scoping rules that apply here. And we're going to call our initializer, create that variable I, and assign it the value 1 inside of this block. Whenever we have a for loop, that iteration variable, it always is created within the loop block. We don't have access to that outside of the loop. And of course, there are always exceptions. If you use var in JavaScript, you'll have access to that outside. And Python has some weird scoping rules where we'll preserve those variables in some cases. But for our purposes here, that is inside the loop block and will get destroyed when this block ends. Now we reach this variable result. We're calling a variable result by name. We're not declaring it. We're not creating a new variable. So now the machine has to figure out what is result? What is this variable? So it's going to start a search. It's going to start within the current block that we're in. Look for a variable named result. In this case, it's not going to find one. So once it doesn't find that variable within the current block, within the current scope, it's going to expand that search to the next outer scope. So it's going to expand this search to the whole stack frame in this case. It's going to find result right here, and that's the variable that's going to be modified. It's going to say, I found result. If I said result equals 3 and then did this is going to modify that result that I created within the block. Since I didn't create a result within the block, it's going to go outside the block, find this result, which was this one, and that's what's going to be modified. So when I run that line, multiplied it by 1, but this is the result that was used. Get to the next iteration of the loop, call the I++ at the end of that iteration. I is now 2. Our conditional is still true, so we're still executing the loop. Now we're going to hit this line, and result is multiplied by 2. So that's the result that we get, that we are modifying. and it's using these scoping rules from blocking. That's how the program is figuring out which variable to modify. Now, in most cases, just give your variables unique names. That'll answer all your scoping questions. But if you do have variables with the same name, scoping rules apply. And we're going to keep running through that loop. I won't go through every step of the loop, but we're going to keep running through that loop until our condition is false. Result is going to store 120 at this point, and we're going to reach the end of this for loop. As soon as we reach the end of the for loop, every time we hit a closing brace, we're going to delete everything in that block that was created in that block. So we have this beginning of the loop block. Anything that's declared after that, it's gone. All of that is going to be erased as soon as we hit the end of the block. Now we reach our return statement. We're going to return the value in result. Result, within this stack frame, there's only one. We're going to return that value 120 from this. Now we reach the end of this method call. We're reaching the end of the stack frame. So this entire stack frame is going to be destroyed and replaced with that value 120. We're returning 120 from this stack frame. So all of this whole execution environment effectively is gone, and we're going to return 120 from that stack frame. So this whole method call here, or function call in this case, is being replaced with the value 120. No semblance of that stack frame exists anymore. It's completely gone. And we're going to set n equal to 120 at that point. We create a new variable n, 120, print n to the screen. We reach the end of this block. Once we reach the end of our program, the end of our main method, we're going to free up all of the memory. We're going to go back to our OS and say, hey, we're done with this program. You can have all of that memory back that you gave us for the stack. And there's no memory of this program ever running. It's not on our RAM anymore. It's just gone. Objects. Oh, I'm in the wrong week. So let's go to this code, and we can make a few changes here. Let's first run this, verify that it does do what I claim it's doing. It does print out 120. Now, if we have a new say we do what I was saying before, I have to make this a var. That's not how anything works. If I create a new variable named result within this loop, this is actually valid. I can do this. I can reuse the name result. The only warning it's going to give me is this could be val because it's never changing anymore. So I can change that to val. But it does allow me to do this. But now when we get to result star equals I, since there's a variable named result that was declared inside of that block, the program never looks outside of that block for a variable named result. There's no naming conflict. I have two completely separate variables because they're in two separate blocks, which I couldn't do. For example, I can't do this. But kind of resolve symbol. It's weird. So I can't do this, but since they're in different blocks here, I can declare result, but this line is working with this result. This one has never changed. When this block ends, this result is destroyed, and this result that's returned is just 1. So I never modified that original result, but that's the only one I had access to during the return. So that's the one that was returned. Similarly, I can create a variable I here. And this actually won't mess anything up. Since that's outside of the scope, when I'm iterating using that variable I, my program never finds this I outside of the loop because it's not in the same scope. It already found a variable named I within the block, so the program's already happy, it already found its I, everything's resolved. There's no need to go searching around for another I. We already have a perfectly good I inside the loop block. Any questions while I'm in the code? Anything you want to see tried? Cool. All right, so that's stack memory. We have two different types of memory for our programs. That's stack memory. And anything that's what we call a primitive type is going to go on the stack. That includes double, float, int, long, short, char, byte, and boolean. And that's it. It's a complete list. There's always an asterisk. There's always exceptions to the rule. You can't actually define new primitives in Scala. It's awkward, and sometimes it's just weird. But for our purposes, these are the only things that go on the stack, which conveniently all the variable types that I used were these types. Notice that string isn't even on this list. But so anything else, everything else does not go on the stack. Everything else is going to go in what's called heap memory. So what is heap memory? I'll at least give the quick intro today. Then we'll go through this example slower next time. So, oops, I meant to delete that slide. But what if our data needs to change size? So for example, you allocate memory and put a value on the heap, or sorry, on the stack, and you put another variable right after that on the stack. Well, what if this variable needs to expand? What if it needs more memory? Or what if it just needs any flexibility? What if I want to delete that variable? I really can't do much with the stack. I get that chunk of memory that I asked for, and that's it. I can't have gaps in the stack, or else things start breaking down the way programs are implemented. So what if our data needs to change size, or what if in general we just need more flexibility? So for this, we don't actually store anything except those types on the previous slide, which are fixed length. Those all have fixed defined number of bits for each of their representations. What if we don't have that? We're going to put those values on the heap. So now, instead of storing my variables on the stack directly, I'm going to ask my operating system for some memory anywhere else on my RAM stick. Could be anywhere on any one of the sticks in my machine. I'm going to ask for enough memory to store my new variable, my new values, and store my values there. And then I'm only going to store on the stack a reference to that value, to that memory address. So all I'm storing on the stack here is going to be the location in memory where I can go to find that value that I created. So if I create an object, which is any object that we create is definitively not one of those that I listed. It's not a double, char, or long, int, short. It's not one of those. So it's going to go in heap space. So when I create a new object of a type that I created, my operating system is going to give me memory anywhere else on my RAM. We don't know where, we don't care where, but we're going to get a reference to that location. And when I store that value in a variable, I have a variable named data, what that's going to store, what that variable actually stores is only the reference to that object. So this is effectively instructions of where it can find the actual information, where it can actually find that object. It is not the object itself. So when we call a method, we start a new stack frame and call a new method. What we actually pass to that method is not the object. It's not the entire object, and we touched on this on Friday. It's not the entire object. It's not a copy of that object. Last time I did say it's the entire object, but we're getting in more details now. We're going to pass a reference to that object. So inside this function, we have that same reference that refers to the same chunk of memory, the same memory address as the other variable, but that's all we're passing. And when we change the state of this object, we're actually going, in this method, we're saying input, which stores this memory address, access this memory, go over to this memory, find a variable named stateVar, and increment it by 1. Now we can see this change from our main method because we didn't just change values on the stack inside the stack frame. We actually went to that memory and heap space, changed a value in that object, and that value is going to be seen even after that stack frame is gone. We're still going to see that change because next time we say, hey, data, access your memory location, go over here in memory and access stateVar, well, that change is reflected because that change was made in heap space, not on the stack. And hey, we actually did get through the slides. I might go over that one a little slower next time. But with that, have a great day. See you Wednesday.